Fine. Feel free to ask me any questions you might have while we're waiting if you'd like. Still got about 7 minutes before class starts.
Hi, Professor. Um, I had a few questions. My
Okay.
first one was I'm unsure how we were supposed to be solving the written problem on our exam, the one about using Gauss's law to prove the equation.
Mm-hmm.
Uh, can you just go through that problem? Because
Yeah. Yeah, there's a lot of videos of it on my YouTube channel too. Just do a search for the word paradigm, Paradigm, and that'll bring up a bunch. But let me go ahead and show you with my screen what we're supposed to be doing.
awesome, thank you.
No problem. So the idea is, I know the screen's not up yet. I'm talking while it's getting loaded or whatever. So the idea is you're supposed to use Gauss's law to compute the electric field. In principle, that could be Gauss's law or Coulomb's law, specifically for a single plate. And then you're going to put two single plates next to each other, one positive and one negative, and compute the electric field between them. Then you got to use V equals the negative integral E dot dl to calculate the voltage difference between the two plates, and then you use C equals Q over V. That's the three-step process. So let me show you what I mean by that. So first off, what I'm talking about doing is imagine an infinitely large plane like this. Okay, only it's infinitely large, so it goes out to infinity. And we're going to imagine that it has a charge per unit area sigma. Now I'm going to put a coordinate system on it like this. So this will be my x-axis, this will be my y-axis, and then the z-axis will be perpendicular to the plane like this, okay? And in so doing, I'm going to use Gauss's law, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's what we're shooting for. Okay. Now, for a Gaussian surface, remember that integral there on Gauss's law has a circle on it. That circle is to remind us that Gauss's law only applies to a closed surface. So if you don't actually literally choose a surface that has a clear inside and outside, then it's not accurate. You can't use that equation. So what we do is, in some cases, we'll take a Gaussian surface to be like a cylinder, like this case. So you can imagine a cylinder, and then it goes through the plane and has a bottom on the bottom side. I mean, has a face on the bottom side as well. So that's our Gaussian surface. And the reason I chose that is I know if I look at a microscopic level, if I take one spot on the plane, it'll have an atom here, which could be charged because the electron's missing. It'll have an atom here and an atom here. And therefore, the electric field due to that middle atom will be pushing up. Due to this one, will be pushing that way, but due to this one, will be pushing that way. So all of them tend to cancel each other out so that the electric field, at least parallel, meaning at a constant z, should be about constant and should actually be perpendicular, i.e. parallel to the z-axis. So we make our hypothesis. We'll say, here's our hypothesis. E is equal to some E of z k hat for z greater than 0, and then some negative E of z k hat for z less than 0. That's our hypothesis. Now, I'm not making the assumption that it doesn't depend on distance. I'm actually allowing the z to be in there. I just don't expect it to depend on x or y, because x and y, if you go to the right a little bit, that would be in the y direction. There's an equally big charge to the left that's going to cancel out whatever the charge to the right did. And the same thing if you come forward, that's the x direction, and then right behind it is the negative x direction, and those are going to cancel each other out. That's why from symmetry we don't expect it to have any dependence on y or x, but we do expect it to possibly depend on z, which is how far we are from the plane. Okay. Now, when you talk about an infinite plane, it really is somewhat arbitrary to talk about distance. So you might even guess a priori what the electric field is going to be like, because how far can you get away from an infinite plane before you start to feel like you're really far away from it. So anyways, let's start off with that. So what I'm going to do is I'm going to say that the dA on, I'm going to get another color here. So the dA on the top here is going to be some little shape like that. So I'm going to say dA top is equal to dA times k hat. And I really don't need to be any more specific than that. So that's what I'm going with. Actually, I got a couple people come in, so I just want to click on it. Okay. Similarly, down here at the bottom, we're going to have another dA. That's going to be dA bottom. That's going to be negative dA. Oops. That's going to be negative dA k hat, because it's got to point down. Remember, the rule is it's arbitrary. Once you choose perpendicular to the surface, it's arbitrary whether it's in or out. But what we decided by convention was that the dA vector should always point as if it's coming from the inside going to the outside. So I know it's that way. Now we also have to do a dA for this little side of the cylinder, and maybe that looks like that. And I call that one the dA soup label. Okay. Now that one's going to have I hat and J hat in it, but that's pretty much close enough for what we need. Okay. Because you can tell when you go to cross product, or excuse me, when you go to dot product that with the electric field, which only acts in the K hat direction, you're going to get 0. So now we start with the left-hand side of Gauss's law. Left-hand side, the closed integral E dot dA. That's going to be equal to the integral over the top of E of Z K hat dotted with dA K hat plus the integral over the soup label, and that's where I'm treating the cylinder like it's a soup can. So the top is the top of the can, the bottom is the bottom of the can, and then the outer surface of the cylinder is the soup label. That's going to be plus or minus E of Z K hat dotted with dA soup label. But remember, dA soup label is like some number, let's say A, I hat, plus some number B, J hat. That's a general form of what dA could be. So that'll come in handy when I go to actually compute it. And then I've got one more term. Whoa, one more term. That's the integral over the bottom. In this case, it's negative E of Z K hat dotted with negative dA K hat. Okay. So I'm going to go ahead and put the equals over here just to reclaim some of the material. And what you see is that on that top surface, E of Z has a fixed value because that top surface has a fixed Z, and E of Z only depends on Z. So I can say E of Z integral dA K hat dot K hat, like that. Then I can say plus this one we're going to see is going to be an integral of plus or minus E of Z K hat times dA soup label, which is just a magnitude, times like A I hat plus B J hat dotted with K hat. Ooh, actually, I could have done that the other way. Let me go ahead and fix that just to make it a little more certain. So what I'm going to do is I'm going to erase this K hat and just act like we're going ahead and taking the vector part now. Okay. So what I'm doing now is, and actually I might as well do that too. So I'm going to say E of Z times dA soup label, but then I have the K hat from the plus or minus E of Z, and that's going to be dotted with A I hat plus B J hat, which you can see hopefully that this quantity is zero because K hat dot I hat is going to be zero and K hat dot J hat is going to be zero. Now I continue on with the bottom part. So I'll say plus E of Z. Notice I had a minus E of Z K hat and a minus dA K hat. So those two minuses canceled each other out. I should put a T here for top soup label for that one. And now I'm going to have BOT for bottom. And now I have dA K hat dot K hat. Now we know K hat dot K hat is 1 times the cosine of 0 degrees, which all of that's equal to 1. So this one's also 1. And this whole one right here is 0. So ultimately the left-hand side becomes 2E of Z times the area of the top. So we're saying that top area that we see of the soup can is what that A is. So top of can. Okay. And remember, the top of the can and the bottom of the can are identical. So me saying top of can covers both of them. So that's the left-hand side. Now the right-hand side is just Q enclosed over epsilon naught. And of course, we have a very specific closed-in surface. We have an area that we called A, and we had a charge per unit area sigma. So the area enclosed contains exactly sigma times A charge. Does that make sense to everybody? Anybody have a question on that? Now I can say left-hand side equals right-hand side. And that's going to give me 2E of Z times A is equal to sigma A over epsilon naught. And of course, these A's cancel out. And we finally can go back to our hypothesis and say that E is going to equal sigma over 2 epsilon naught K hat for Z greater than 0 and negative sigma over 2 epsilon naught K hat for Z less than 0. That's what our electric field is. So that's the Gauss's law portion that we had to do. Now we're going to take those two plates, or actually going to take one that's positively charged with a charge of sigma positive and then another one of negative sigma. And we're going to put them next to each other. So in profile, that looks like this. This is one that has positive sigma. And this is one that has a negative sigma. Okay. And it might even help to label the negative one red so we can make some sense out of what we're doing. So what I would like to know right now, this is part of what you're supposed to be doing, is you're supposed to figure out at this dot, and then at this dot, what is the direction of the electric field due to just the blue plate, the positive plate. So on the far left, which direction will the electric field point on the left? Remember, the electric field points in the direction a positive charge will be compelled to go. Shonda, do you know on the left there which direction the electric field is going to point? To the left of that blue plane? Forget about the red one. Pretend it's not even there. I'm just picking on you because your face showed up. Sorry.
It's gonna go to the right.
Uh, not for the positive plate. It's going to go to the left because that's a positive plate, and the electric field points in the direction a positive charge would go.
Oh, sorry, I was thinking about in the middle.
Okay, yeah, okay, gotcha. That makes sense. In the middle, it's definitely going to be to the right. You're right about that. And what about on the right hand side? Would you agree that it also points to the right on the right hand side? Or do you think?
Yes.
Yeah. So that's key. Now we can do the same thing for similar dots for the red plate. So again, we're just forgetting about the existence of the blue plate. Which direction does the electric field point on the far left-hand side? And I might have been saying left when I meant right, or right when I meant left. So I apologize if that was the case. But this one, hold on, I got something.
Oh, I was thinking about all the plates like together. Yeah.
Yeah, what about this guy? Which direction would the electric field point there?
To the right.
To the right, because it's a
Yeah.
negative plate. And what about this guy?
Towards the negative plate.
Exactly. So it'd be like that again. Oops. Evidently, you got to take it off your little laser pointer when you're doing that. And then over here on the right hand side, which way would it point?
Yeah, left towards the negative plate.
Exactly. So what you see is, notice they have the same magnitude, sigma over 2 epsilon naught, but between the plates they add. So what we get is E negative plus E positive is equal to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which is sigma over epsilon naught. That's the electric field between the plates. Out here, though, you see E equals 0, and out here, you see E equals 0. Now, we've got the electric field between the plates. It's sigma over 2 over epsilon naught. And now we want to calculate the electric or the voltage from one plate to the other. So what I'm going to do is I'm going to imagine integrating. I'm going to draw these plates again. Let's draw this plate. And that's going to be my positive sigma plate. And then I'm going to draw another one over here. Now I'm zooming in on it really, really close. That's why I look so far apart. They would actually be very, very big in this frame. And what I want to do is I want to integrate from here to here, and this distance I'm going to call D. Okay. And in fact, what I'll do is I will draw a coordinate system. I meant to draw that in black. That did not help. There's my y-axis. And let's say this is my x-axis, and the origin's right where that plate is. So what we know is delta V, which is VB minus VA, is equal to the negative integral of E dot DL. That's that line integral. And just to make sure everybody knows what we're talking about, this is going to be A, and this is going to be B, which I'd said was lowercase, so I should draw it lowercase, like that. So what I know is I got the negative integral. I know the electric field, in fact, points to the right, so it's going to be sigma over epsilon naught. In this case, we're going to call it pointing in the negative I-hat direction, because I just drew that coordinate system. It wasn't like that before. And then I'm going to dot that with the direction I'm going. So I'm actually going to use the DL to indicate the direction I'm going. So that's going to be a negative DX I hat, like that. And now, since I've chosen that one, I just go from small coordinate to large coordinate in for the range of integration. So my range of integration is going to go from the small number, which would be 0, to the large number, which would be d. So you can see now that I got 3 negatives, so that's ultimately going to give me a negative. The sigma over epsilon naught is going to come out in front because that is, in fact, a constant. And then we're going to get the integral dx I hat dot I hat, which is just 1. And it's going to go from 0 to d. Okay, now in this case, I'm actually going to come out with a negative voltage, but it's okay. As I told you before, it doesn't matter if you screw up and get a negative voltage, just change the sign and go with it. So we're going to get negative sigma over epsilon naught times d minus 0, which is just basically negative sigma d over epsilon naught. So that's the actual voltage difference minus the sign. Okay, so that was part 2. And now part 3 was C is equal to Q over V is the formula for capacitance. So we're going to take a sigma times an area A, and we're going to divide it by sigma times D over epsilon naught. You can see the sigmas cancel out, and I get epsilon 0. That's going to be on the top times A over D. And that's the formula we were looking for the capacitance. Okay. Any questions on that? Now, be advised, just in case there was what I saw on the test, a lot of people made the mistake was saying or realizing that this is the same thing as Q divided by A. And that's right. But then they chose, or they seem to have chose a rectangular box like this for the area. So they then said sigma is Q over L squared, and that's okay too. But then when they did delta V equals negative integral E dot dl, they mistakenly took an integral of sigma over L squared dl. That part is wrong. Okay, so don't do that.
I'm pretty sure that's what I did.
Yeah, a
I think
lot
that
of
makes a
people
lot of
did
sense.
that. Yeah, they
Yeah.
did that, or some of them just ignored the L, and some of them even got the natural log and all that good stuff. So, but that's basically the problem in its entirety. Did that help you?
That was perfect. Thank you so much. But sorry to ask another question.
Yeah, go for it.
I was looking at my grade detail and I noticed that one of my exam grades is showing up as temporary. It was actually exam one. Were we supposed to submit like working? Is that why it's still as temporary?
No, I'll check it out. I remember your last name and everything, so I'll check it out after class. I'd never heard of that before, but I'll double check and see what's going on with it.
Awesome. Thank you so much.
No problem. All right, so let's get started. I wanted to go ahead and finish up what was chapter 27. There's a little bit of stuff we need to cover in there. And then I'm going to jump into 28 where stuff starts getting hairy again. And then we'll find a way to make it easier, just like we did before with that nasty Coulomb's law. And then we made it easier with Gauss's law, in principle at least. We're going to do the same thing with chapter 28. But first off, I wanted you to imagine a scenario. So let's imagine we have a little Axel. You might know him from such groups as Guns N' Roses. No, that's a different one. so, so, anyways, let's pretend like we've got a little axle here. Okay. And then on this axle, there's a little wire that runs across like this and then makes a sharp turn and then goes back like this. Similarly, this one makes a sharp turn and goes back like this. Now, what we're going to do here is put another part of the axle, if you will, right there. And then we're going to allow this little piece of wire to run down the side of that axle. and we can actually just flatten the wire out at that point if we wanted to, and let it touch a piece of metal that just touches another piece of metal, so it doesn't have to wrap around the axle. But the main thing is we're imagining this axle actually spins. Okay, now this is going to be embedded, in fact, in a magnetic field that's uniform, like this. Okay, and I am going to say that this width right here is going to be A, and this width right here is going to be B. Okay, and not only that, I'm going to imagine that there's a current in this wire I that runs around that way, that way, that way, that way, back down here, and in fact from here it goes out, and from here is where it came from. Okay, we're only going to care really about the magnetic field in this little boxed area. But I want you to think about, let's say, this little wire. I don't know what's going on with this now. This little wire right there. Which direction would, if any, would the force on that wire be acting as a result of that magnetic field? Remember, the formula is dF is equal to IDL cross B. So can anybody tell me, is there a force on that little piece of wire?
Yes.
For that one, notice the current is going to the right. This rectangular loop of current of wire that I've shown you is actually lying in the page, and the magnetic field is lying in the page as well. So those two are actually parallel, and if you ever take the cross product of two parallel vectors, you get 0. So for this little part, F is equal to 0. Anybody want to guess what happens for this part? F is equal to 0 there as well. And how about this part? This is anti-parallel. That's still the same thing there, right? So F is 0 on that one, and F is 0 on that one as well. Now we do have this magnetic field acting to the right, and this current right here going up. Can anybody tell me which direction the force would be acting as a result of that current and that magnetic field? Remember what I told you, it's IDL. This finger points in the direction of the current parallel to the wire. This finger points in the direction of the magnetic field, and then this thumb points in the direction of the force.
Is the force going into the page?
It very much
Yeah.
will, yes. Good job. So here, the force is in the page. Okay, what about over here on this part? IDL, B, and then F is your thumb. Y'all see that this one's going out of the page? The reason why I'm pointing this out and setting it up this way is you can see that in this orientation, the wire is actually compelled to rotate. In fact, that side on the left is going to come out of the page, and that side on the right is going to go below the page, and it's going to tend to rotate it. And in fact, you can calculate that torque like this. Remember, torque we normally use torque is equal to R cross F, which you can also say the magnitude of the torque is R perpendicular times F, or you can say it's F perpendicular times R, or you can say it's F times R times sine of theta. But in this case, the R and the F are automatically perpendicular. So we have this axis of rotation right down here. And in fact, both of these tend to make the thing rotate such that the left side comes out and the right side goes below or behind the page. So they're both the same sign. And the torque is going to be the force times the lever arm. Well, we know the force is I times the length times B. So it's going to be I, oops, let me go back to purple. It's going to be I times B, the distance across that, times the magnetic field, which would be B, and then the lever arm, I think you can see, is A over 2. So that's for one of them. And then the other one, I think you can see, is going to be the same thing. I times B, that's the force. Let me indicate that so you can see. There's F. There's F. And then the lever arm is, again, A over 2. So what we ultimately get is I times B times AB. That's not a coincidence. Notice this AB is actually the area of the loop. And in fact, that plays the same role as P does in electric forces and electric fields. Remember, P was equal to Q times D in some sense. And that basically was a matter of, you had a positive charge, you had a negative charge, the distance between them was D. So if you drew a vector that actually pointed from the positive charge or from the negative charge to the positive charge, in other words, the opposite direction that the magnetic or that the electric field would actually point, if you called that vector D, and you call this plus Q and you call this minus Q, meaning they're equal but opposite, then P was the magnetic, or excuse me, the electric dipole. So that was how the electric dipole was defined. Now, what we're going to do is we're going to define a magnetic dipole. That's given the symbol mu, and I'm going to leave a space in here on purpose, but basically the magnetic dipole is the current times the area. So we'd say I times A, and we would let a vector represent the area A, and that vector would be consistent with the right-hand rule. Which means if you let your fingers curl around in the direction the current's going, like in this case, the current's going in a counterclockwise direction. So I would hold my hands like this, lay it on the screen, and my fingers would curl around the same direction of current. My right thumb points out of the page. So a vector would point out of the page for this loop that I've got drawn. Now, the reason I left off or left that space between it and the equals is because sometimes that loop is not a single loop of wire. Sometimes it has N loops, in which case you write N times I times A. So now that we look at that, I think you can see exactly what this torque is. In fact, you can tell that because these were perpendicular and everything, it worked out kind of nicely. So we didn't have any extraneous stuff. But in fact, the torque on a magnetic dipole is mu cross B. Okay. Just like torque is equal to P cross E that we found when we did the electric field and electric dipole. it turns out also that we had U is equal to negative P dot E for the potential energy. Well, guess what? You can do the same calculation here, and you're going to find U is equal to negative mu, dot B. And of course, we ultimately were able to find that the energy density, the energy per unit volume, was in fact 1/2 epsilon 0 E squared. Well, lo and behold, we're going to find this is 1/2 mu 0 B squared. So you can see epsilon 0 and mu are very similar, but they sort of take a reciprocal role where when you're using the epsilon 0, you often have to use 1/mu or vice versa. Okay. So that was one of the major things we had to cover. This is pretty straightforward. It's just like we did in chapter 21 and 22. And I think we even touched it with 23, but hopefully that helps you a little bit. Anybody have any questions on that? You should be able to tell that the units for the magnetic dipole moment, mu, is actually equal to amps times meters squared. Okay, so that's actually what the units are. That's something you need to know, something you can work with, so on and so forth. But now I also need to show you one more last sort of thing. We've already talked about dF being equal to I dL cross B. And I actually motivated that by telling you that F was equal to Q V cross B. And when we looked at the units of Q times V, that turned out to be coulombs meters per second, which turns out to be the same as this, which would be coulombs per second times meters. Okay. Notice in this case, the coulomb per second came from the amps. And in that case, the second came from the meters per second in velocity. Well, we can also take F and consider what happens when we have an electric field and a magnetic field. If we had an electric field, we know F is equal to Q times Z. And if we had a magnetic field, we know F is equal to QV cross B. So if we put these two together, we reach the conclusion that F is equal to Q times E plus V cross B. And this is the Lorentz force law. Okay, and it's just sort of a synopsis of what can happen to a charge. So a charge subjected to an electric field is going to feel a force. A charge that doesn't have a zero velocity, in other words, a charge that's moving, is going to feel a magnetic force. The magnetic force is given by QV cross B. The electric force is given by Q times E. So hopefully that is a pretty good reminder. So if you were to, for instance, want to make a velocity selector, what you can do is you can create a uniform electric field by doing a parallel plate capacitor. This could be a plus, a plus, a plus, a plus, a plus, like that. And then a minus, 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 minus. So this actually creates a electric field pointing downward. I'm going to call that electric field E. Okay. Now, if in addition to that, you create a magnetic field that goes into this page, that also is going to be uniform, of course. That's going to be the magnetic field B. And what you do is you create a little stopper, if you will, that basically only allows a narrow slit for particles to come through. So you could send, for instance, a bunch of positive charges all going like this, but only a very small few would get through because that slit's not going to let it. Okay. Well, when you get in there, here's the positive charge moving that way. So, in which direction will the magnetic force act on this positive particle at this point? So remember, it's QV cross B. B goes into the board. The index finger is Q times V. The middle finger is B as in boy for magnetic field. And then the right thumb is the direction of the force. So which direction is the force acting on the positive charge right there? Just due to the magnetic field. Forget about the electric field right now.
Wait, the force is up, right?
Exactly. So this is the magnetic field force. So I'll say F sub B. Now, which direction is the force due to the electric field? Remember, the electric field points in the direction that a positive charge is compelled to move. So anybody want to tell me which
Oh, that
direction?
will go down.
Down, exactly. So this is the force due to the electric field. So if you want to choose a very specific velocity, you need these two to cancel each other out so that it'll make it not only this far, but you want it to go undeflected through there. So what you need is the magnetic force, which would be Q times V. And notice they're all perpendicular, so I really don't have to use the vectorness of it, QVB. And that's got to be equal to Q times E. With that, you can see the Q's cancel out, and what you get is V is just equal to E over B. So that's how you make a velocity selector. You take a magnetic field that you create, an electric field that you create, and when you divide the electric field by the magnetic field, that should give you the actual velocity. That velocity is the velocity you're selecting within a margin of error, obviously. But basically, you make those slits narrower and narrower, and that gives you a smaller margin of error in principle. If you ignore quantum mechanics, if you start taking the quantum mechanics, other things happen. But either way, that's a velocity selector. So that's one application, and it's extremely helpful, and you'll see that in your book. Now, another one is a mass spectrometer, and basically, with that, you can call it a mass spectrometer, but you can just also think of it as, hey, I would like to separate things based on mass. For instance, when we were trying to develop a nuclear weapon, we knew that uranium 235 was decent, but it wasn't great at creating the necessary conditions that we needed for a nuclear weapon and later even nuclear power. So we discovered that the uranium isotope 238 was the valuable one. So what we had to do is figure out a way to separate uranium 235, which is readily abundant, from uranium 238, which is extremely rare. So if you manage to ionize a nucleus of a uranium, of a bunch of uranium, then something like 1 in 10,000 would be an actual uranium-238. If you then sent it ionized in through a mass selector type mechanism, then the one with the heaviest mass would make the smallest radius turn, or excuse me, the largest radius turn. The heaviest one would basically make a big circle, and the lightest one would make a small circle. So if you had a port that could catch the things that made the big circle, you could get the uranium-238 to follow that. Uranium-237 would go somewhere else. Uranium-236, if that existed, go somewhere else, and 235 would go somewhere else. So how do you do that? Well, in that case, you make use of the force for magnetism, which is QVB. Of course, it's QVB sine theta, but we always set them up perpendicular, so you can just get QVB. And you say, according to Newton's second law, the summation of the forces is equal to mass times acceleration. So in this case, we're going to set that equal to m, but we're trying to make a circle. And does anybody recall what acceleration you have to make something go in a circle?
Are you talking about like v squared over r?
Exactly, that's the
Yeah.
one. V squared over r. So if you set that up that way, you can immediately see that one of the velocities cancel out. And ultimately what you get is, you get that the radius of the circle that's going to happen is equal to mv divided by qb. So that's the actual radius of a circle, not unlike the magnetic deflections lab that you guys did. Now, if you want to go further, you can say, okay, well, I know this velocity is going to make a circle, so I know the velocity is going to have to equal 2 pi times the radius over the period. This t is called the period. Okay. If I wish to, then I could replace the v with this quantity. And when I did that, I'd get r equals m over q b times 2 pi r over t. And you can see again that the r's are going to cancel out. That r cancels out with that. And you could ultimately say that t, I'm going to write it in purple now, that t is actually equal to 2 pi m over qb. And of course, the frequency, which is 1 over the period, would be qb over 2 pi m. Let me make sure all my arithmetic and algebra is right here. T goes over there. That looks good. 2 pi m is on top. QB's. Yeah, that all looks good. So these are the equations you'd use if you wanted to actually make, for instance, a cyclotron, which was the original particle accelerators. Basically what they had, because we're lucky enough that this formula for the period, notice that doesn't depend on the velocity. So because of that, we could actually take a stream of particles moving at some velocity v and have it attracted, say if it's a positive particle, we'd have it attracted to this by making it negatively charged. And of course, it would get into a magnetic field that we had set up in this thing, and it would come back around here. And then we'd take this other D, which is, they call them the super Ds, but we'd take this other D, and now we'd make this one at just half of a period later, we'd make it look negative. So that would cause the particle to speed up a little bit across here. And then, of course, it would make that path around this way, and we'd flip it back to a negative again. So that's what allowed us to repeatedly accelerate just during that gap part, the particles. And these are the equations you use for that. Anybody have any questions? So these are supposed to be really, really straightforward, easy equations. You're not supposed to have to derive them necessarily. If you can, that would help you even more because then you'll never forget them. I mean, I never memorize these equations because I just derive them. And every time I use it, I just rederive it again. So that actually works really well. Of course, you can't do that really with the F equals QV cross B or the IDL cross B necessarily. Those go on memory, but these other ones you can use. Anybody have any questions on that? Okay, so we've already used a few facts. Like we did find that the force on a current carrying wire was mu 0 I1 due to another wire I2. And we'd say force per unit length over 2 pi r, where r is the distance between them. We found that. So that's a fact we already knew. But in order to do that, we had to know F equals IDL cross B, which we did. But we also needed to use the equation for the magnetic field created by a current carrying wire. And that equation was B is equal to mu 0 I over 2 pi r, where mu 0 is 4 pi times 10 to the negative 7th Tesla meters per amp. So that stuff we already used, but I gave those to you with basically no evidence, no proof. Now we're going to do that with chapter 27 material. So that was all chapter 26. Now we're going to do chapter 27. Anybody need to ask me anything before we start into chapter 27? So this is going to be called the law of Biot-Savart. Okay, and that's just a section within 27. 27 is called sources of magnetic fields, but I'm starting off with a different section. Okay, it turns out that basically by trial and error and experiment and just brilliance, the law of Biot-Savart was created, and it basically says that dB, a differential bit of a magnetic field, is actually equal to mu 0 I over 4 pi times dl cross r hat over r squared. Okay, that really, really, really needs a diagram though. So let me show you what the diagram would be. So this is a current carrying wire, for instance, and it's carrying a current I. And we could imagine, for instance, right here is a vector dl. Notice that has to point in the same direction that the current is going. And if we would like to know the magnetic field at this point right here, P, then what we need is to draw a vector from here to there. Okay, so that's really what the r vector is. The r vector is supposed to be a vector that points from dl to the point at which we wish to know the magnetic field. The r is the magnitude of it, and when I put a hat on top of it, that means it's a unit vector. So you got to find that vector and then compute the unit vector by dividing it by its magnitude. Now, there's a couple ways you can think about that. What I normally do is I'll take my students and I'll say, okay, let's draw a little coordinate system like this. And I'll draw a chunk of wire going around like this. And I'll say, okay, well, this is the r dl vector. That's the vector that points to the little section dl of the wire. And then there's another vector that points, say, to P, which is the point at which we wish to know the magnetic field, like that. And then this little vector, I'm going to use red, this little vector from here to here is the R vector that we're talking about here. So you can see that the R vector is actually RP, meaning the vector that points to the point, minus RDL, which is the vector that points to the differential charge element. So you can use that as well if you need. I think the bigger part is for you to just figure out how to use this in general. So I'm going to jump right in and do a problem for you. So let's, I'm going to draw a coordinate system. And my coordinate system is going to be this. That's going to be my x-axis. Let's let this be my z-axis, just because I can do something that's kind of helpful. Then I'm going to draw my wire. So there's the left edge of my wire. There's the right edge of my wire. And the current I is going up. Okay. Now, what I wish to do is at this point P, I would like to know the magnetic field strength and direction. So that's really what we're shooting for, and we're going to use the law of Biot-Savart to do it. Okay. So as I told you, the DL goes, it basically stays along the path of the wire and always points in the direction of the current. So what I'm going to do is say that this little vector right here, or excuse me, this little chunk of material right here is DL. And you can see, in fact, that distance would be, darn it. That little distance would be DZ, say. And I want the vector, of course, to point in that direction. So that would be my DL vector. And we'd say DL is, in fact, equal to DZ K hat. Does that make sense to everyone? Now, if you want to use the little red vector that I just showed you, then what you would do is you'd say, okay, well, this little vector points from the origin to DL. So this little vector is RDL. And I think you can see that that would be ZK hat. And then there's another little red vector that points from the origin to the point. And that's this little vector right here, which we'd call RP. And of course, that one is, let's say, some distance X, and it points in the I hat direction. But for actually, just because we use the formula and we're expecting it to come out in terms of R, I'm going to not use X. I'm going to use R there. That's part of the reason why I chose to write that axis, that vertical axis, as the Z axis. So I'm just saying this distance from here to here is R. Okay. So if you want to use these red vectors, it's pretty straightforward. I will say RP, as we said, was actually equal to R times I hat. And then we said RDL was equal to Z K hat So these two combine to tell me that R is equal to R I hat minus Z K hat. Okay. Now that also means, I'm going to draw this vector in black this time. That also means that this vector right here, that's the actual R vector in the formula. So that's the R that we, in principle, just calculated with Ri minus Zk hat. It's also the one in the formula, but you can see now how it works. So now I can say B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl. Now our dl vector is dz k hat. That's going to be crossed with, now this is also something that's kind of funny. If we wanted to, we could leave that vector as r hat, and that means we're going to have to take the time to compute the unit vector that represents r. In other words, we calculate r, which I just did. I find the magnitude of it, which is the square root of r squared plus z squared. And then I take r, the vector, and multiply it by 1 over the square root of r squared plus z squared, and that's r hat. But another thing we could do is we could just say mu 0 I over 4 pi dl cross r over r cubed, and that would fix it all. So that to me is a much smarter thing to do. I'm going to just go ahead and write it times dl cross r. I'm going to go ahead and use the r, which is r I hat minus z k hat, and then all of that is going to be r squared plus z squared, and now the square root of that is really what the power is, and the square root is an exponent of 1/2, but I'm going to cube it, so it's going to be a 3/2. That's the actual integral we're going to calculate. Can anybody tell me, just looking at this and knowing the right-hand rule that you already learned about the magnetic field caused by this wire, in which direction would the magnetic field point right there at P? Your choices are to the right, to the left, up, down, into the page, or out of the page. We're wanting to know the direction of the magnetic field at P due to the current I. Answers are right, left, up, down, into the page, or out of the page. Anybody? Remember, you're supposed to put your thumb in the direction of the current, which
Is
is
that to the left?
almost. I see where you're going, but notice how my fingers curl around, and it's always got to be sort of tangential to the circle that your fingers make. So right here to the right of the wire, the circle would have a tangent line going into the page. So it's actually in the page, which I think you can tell is really the theta hat direction, which is why I chose to make the Z axis the vertical one. But that's really what we're going for, is that theta hat direction that we know from spherical and polar coordinates. All right, now DZK hat crossed with RI hat and ZK hat, that seems like a nightmare, but it really isn't that bad. Really, all we got to think is the cross product is also a linear operator like the dot product is. So I can take this mu 0, I don't know why I started writing in black, but it seems like that's what I'm doing, times 4 pi times the integral. Now, what we're going to have is dz times r, and then that's going to be k hat cross I hat. Notice how I didn't change their order. And then I'm going to have minus z dz k hat cross k hat. So that's like using the distributive property, but the distributive property for a cross product. So if you take your normal coordinate system, which remember is right-handed, so that means if this is my X coming out of the page and that's my Y to the right, then I have no choice but to make my Z go up. Okay. So if you look at that and you try to do the cross product using your fingers on K hat cross I hat, you see K hat's the up direction. I turn this around this way to show the I hat coming out of the board, and you see that actually points in the Y hat direction. So K hat cross I hat is really the J hat direction, which by the way is into the board. So I'm going to say equals mu 0 I over 4 pi times the integral of r dz j hat. Now the k hat cross k hat, that's just 0. So that one completely disappears. And what I have left down in the bottom is, of course, don't know why I switched colors, is r squared plus z squared to the 3 halves. Okay. And I've got to integrate this from z approaching negative infinity, because it's an infinitely long wire, to positive infinity. And that seems like a nightmare, of course, but it's really not too bad, because I'm going to say, I really tried to change colors that time. Let z equal r tangent theta implies dz equals r secant squared theta d theta, and z equals r tangent theta also can help you by looking at it this way. If you say this is the angle theta and this is z and this is r, then you can see tangent theta is z over r, and this part over here would be the square root z squared plus r squared, which is going to come in handy in a few. So now that I have that substitution, this is called a trigonometric substitution, I can say B is equal to mu 0 I over 4 pi times the integral. Now dz is just going to become r secant squared theta. So I had an r there already, so now I got an r squared secant squared theta d theta. The j hat plays essentially no role but giving us a direction, by the way. And down here in the bottom, we're going to have r squared in both terms because z is equal to r tangent theta. So I'm going to factor out that r squared, and I'll have left 1 plus tangent squared theta, all of that to the 3 halves power. Everybody see that that's the 3 halves power? Let me try to make it a little clearer. Okay, so that's all to the 3 halves power. Now, what the r squared in the top and then the r squared in the bottom and the 3 halves, that's going to make r cubed on the bottom. So with this, we end up getting mu 0 I over 4 pi. Now remember, it's r squared in the top and it's going to be r cubed in the bottom, so it'll just be an r in the bottom like that. But 1 plus tangent squared is secant squared. And that secant squared is raised to the 3 halves power, so that's going to be secant cubed theta under secant squared theta d theta, all that times j hat, like that. And lo and behold, you obviously are getting rid of all of the secants except for one in the bottom. And of course, 1 over secant theta is cosine theta. So I now get B equals mu 0 I over 4 pi r times the integral of cosine theta d theta. Now I'm supposed to integrate from z equals negative infinity, which I think you can realize is negative pi over 2, to positive pi over 2. Of course, cosine is an even function, so I can just multiply that by 2 and just go from 0 to pi over 2, and that's what I'm going to do. So I can say this is equal, and I forgot my j hat again. So I can say this is equal to mu 0 I over 4 pi r times 2 times the integral from 0 to pi over 2 of cosine theta d theta j hat. Of course, the derivative of sine is cosine, so the integral of cosine is sine. So what I now have is mu 0 I over 2 pi r times the sine of pi over 2 minus the sine of 0 times j hat. And of course, the sine of pi over 2 is just 1. So ultimately, I get B is equal to mu 0 I. That's a really bad mu 0. B is equal to mu 0 I over 2 pi r. And in fact, remember this right-handed coordinate system, I hat is in the index finger direction. K hat is supposed to be in the thumb direction. When I do that, you see that J hat has to point into the page, which is exactly the direction of theta hat. So I'm going to call this theta hat, even though in this coordinate is also the same as J hat. But you notice you can rotate this coordinate this coordinate system by any angle you want about the z axis, and you always get J hat for the direction. So that's the other part of the proof that shows that it is actually in the theta hat direction, not the j hat direction. And that's it. We managed to show that B is in fact mu 0 I over 2 pi r. Anybody have any questions on that one? That's a tough one. That's the nastiest thing you'll see in this semester or last semester, and even if you took a third semester of this course, as a lot of schools offer, where it's nothing but modern physics, I don't think you'd run into any more complex mathematics than that. At least I never taught any more nasty or more complex than that. Anybody have any questions? All right, so there's another type of problem you can also solve with that. That one's sort of the nasty of the nasty, but you can also do like a current loop. Like if you had a circular loop of wire, you can actually calculate that as well. So let me attempt to show you. Well, we don't have much time. Well, we got what? It's supposed to go till, no, we're supposed to go till 6:40, right? So we got about 14 minutes. Yeah, I think that'll work. So let me draw another coordinate system. Again, I'm drawing the coordinate system specifically so you don't have to, but that's not the norm necessarily. A lot of times you're going to have to come up with a coordinate system yourself. So just keep that in mind. This is going to be my x-axis. This is going to be my y-axis. This is going to be my z-axis. And what I'm going to do is imagine a current carrying loop of wire, let's say like that, okay? We'll see if I can actually move it a little bit to the left. It's not lined up like I like. Yeah, that's probably good enough. Right about there. Okay. So what I'm saying is this distance right here is going to be R. And what I'd like to know is the magnetic field at this point up here, which I'm going to say is a distance Z above the axis. Okay. Now, what we can do is we can imagine a little differential element right here. I'm going to draw it in black. So that's my DL vector. Now, technically, this would be the RDL vector, which you don't necessarily need. That was that thing where I told you if you wanted to use the red vectors, you could. And then this, of course, would be the RP vector. What you really need, though, is this vector right here, which I'm going to draw in red this time, which points from the DL to the P. That's the R vector that the law of Biot-Savart is actually using. Okay, and P is where we want to know the magnetic field strength. But look, notice it's right along the axis, so that makes it a little easier. Just to finish up where I show you that R is equal to RP minus RDL. I'm going to go ahead and show you what that is. RDL, I think you can see, you could say that's actually R. Well, let me go ahead and do it bit by bit so it don't seem so awful. So I'm going to say RDL first. I can call this angle theta. And then I think you would agree that the x component of RDL would be R cosine theta. So I'll put an I hat next to that. And the y component would be R sine theta. So I'll put a j hat next to that. And then RP is really easy. RP is just Z K hat. So when I do R, which is RP minus RDL, all I'm going to do is say ZK hat minus R cosine theta I hat minus R sine theta J hat. That's the whole vector. And the best part about it is it's really easy to deal with. And if you go to calculate the magnitude of it, it's just Z squared plus negative R cosine theta squared plus negative R sine theta squared square root. Well, I think you can all tell that that's just the square root of Z squared plus R squared. So that's kind of nice as well. Okay. Now I could have just started from that and worked out what RDL is or what the R is, but this is a case where it's not that easy. That's why I like actually having the subtraction formula. So I went ahead and did it here. So now we can say B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of, now we're going to take a DL vector and cross it with what I told you was R, in fact, happens to be RP minus RDL. And I'm going to do RP minus RDL magnitude. And rather than make it a unit vector, I'm just going to put a 3 on there and that fixes it. So that is what I think is the most useful version of the Biot-Savart law. That's it written out in all its beauty and stuff. So if you can keep track of that, that would be a good one. I think I even listed on that way on our equation sheet. So now I can go ahead and say B is equal to mu 0 I over 4 pi. Now my DL vector is going to actually be equal to, I didn't write that down. I'm going to say R, or excuse me, I'm going to say DL is equal to R d theta. And that's going to actually point in what I call the theta hat direction. So we can do that, and I can actually work out what the theta hat direction is for you guys. We might even have to do it, but usually you can just take a cross product and never have to deal with it. So let's see right now. I got mu 0 I over 4 pi. That's going to be the integral of R d theta, theta hat, crossed with, now I'm going to take the cross product of z k hat minus r cosine theta I hat minus r sine theta j hat. All of that is that big nasty vector. And then all of that's going to be divided by z squared plus r squared to the 3/2 power. Okay. So if you do theta hat cross k hat, I think you can see theta hat pointing in the direction of DL. Theta hat cross k hat, they're automatically perpendicular to each other. So it goes basically theta hat's this way, k hat's this way, excuse me. Theta hat is this one, k hat's this one. So the cross product actually points radially outward. That means that it's going to actually be the r hat vector. So I can write over here, I can say theta hat cross k hat is equal to r hat. And r hat is actually cosine theta I hat plus sine theta j hat, which I can derive for you as well. But that's actually what it turns out to be. What you also might notice is I'm going to have to integrate this over d theta from theta equals 0 to 2 pi. And I think you all can tell that right now where the vector's drawn, it's actually going to create a dB vector that's sort of like that direction. But notice when I get back here, it's going to make an opposite one where the X and Y components are going to cancel each other out. So what happens is I know for a fact that this guy and this guy is going to integrate to 0. Notice I just drew an integral symbol and then an arrow 0. So that's really what I expect is going to happen. We're going to carry it out and see how it plays out. Next line is mu 0 I over 4 pi. We're running out of time. This is going to be the integral of r d theta, and then theta, or excuse me, r z d theta, because I went ahead and used the linearity of the cross product. I pulled the z in front of the d theta, and the theta hat cross k hat gives me the r hat. And then the theta hat cross I hat, they're actually in the same plane. That's still going to go to 0. So it doesn't really matter too terribly much, but basically we can say plus 0 for those. And then all of this is going to be over z squared plus r squared to the 3/2. So I'm going to get mu 0 I times r times z over 4 pi. it looks like the z squared plus r squared is not going to be partaking in this integral either. So I get the integral of d theta. And this can't be r hat. Uh-oh. Theta hat cross k hat. That's definitely r hat. But that's not the direction the magnetic field should point. The magnetic field should actually point in the direction of dl cross. Oh, okay, it's going to be like that. Okay, gotcha. We'll be in an r hat direction. Yeah, so that's right. Okay. So now that I got that, I've got the integral of d theta r hat, and that's from theta equals 0 to 2 pi. So ultimately, this gives me b is equal to mu 0 I over the d theta. When I integrate that from 0 to 2 pi, that's just going to give me 2 pi. So this is going to become mu 0 I over just plain 2 z squared plus r squared to the 3 halves times rz. And all of that will be in the r hat direction. And that in principle should be right. I'm not sure what happened. Something might be funny, but that looks mostly right. I know the answer is supposed to come out to about mu 0 I over 2r. I might have to re-investigate this for next time, but this gives you a good start. Time is up. Make sure you text me your first and last, or you chat me your first and last name before you split. But I will wait for the last person to leave in case anybody has any questions, and I'll figure out what's going on with this and either make a new video or just redo it next time. So have a good one, everybody. Thank you for coming.
Professor,
Yes.
hi. I sent you that email for the late penalty assignments.
Yes. Did you? That's what I was just wondering about, because I remember you said you were going to send me the ones that you were doing, but they were counting them off.
Yeah,
Okay.
I
Yeah.
sent a screenshot of them.
Yep, I have it. I'll go ahead and change them. I'll probably change them tomorrow. I might get a chance to change them.
Okay,
I have visitors, but yeah, I'll definitely get it done for you.
no issue. Thank
Thank you
you.
for reminding me. I appreciate it, because I'm definitely one to forget it.
Well, thanks for being patient with me.
Yeah, thank you for working
Appreciate
with
it.
me.
All right, well, have a good one.
Did you see Brianna? Sorry about calling you hun too. That's a habit.
That's all right.
I gotta
It's
stop.
a term of endearment.
It's supposed
Okay,
to be
bye.
done, but
Have a good one.
you too.
Oh, hey, Professor. I just had a question about like, the grade. I don't think you graded a conceptual 22
Okay,
for Pearson. Yeah.
let me check that real quick. Conceptual 22. I'm looking. It's Micah, right?
Yeah.
Okay.
Yeah. I just don't see like a thing for it at all. Um,
Gotcha. I'm seeing it here. I think it might not be turned on. That might be why you're not seeing it
yeah,
on Canvas.
that's what I was thinking.
But it's definitely recorded here, so I know it's there.
Okay.
Yeah, I see your grade. Yeah, I'm definitely there. So it's just a matter of maybe I didn't turn it on our side. So I'll check the grade book with that now and fix it for you.
Yeah. Um, well, I'm gonna stay on. I just had something kind of cool from like another class to show you. But I guess
Uh-huh.
there guys want to ask you like a homework question, so I'll just
Okay.
hang.
Okay. Richard, do you have any questions, or Kim?
Yeah. Oh, I just wanted to say, thank you for being patient and stuff like that.
You're
For the
welcome, and thank you for being patient with me. I know I had so much going on, I forgot a couple times, but you stuck with it. Good job.
yeah, but I just want to know what was like more convenient, like when it comes like the last test, whatever test for. Would you rather just want me to go to the lab or the testing center? Like, which one would you rather me do?
If you like doing it in the testing center, that's fine. I don't mind at all. Just as long as you let me know the day, about 2 days before would be best. Then everything will work out fine. So whatever's more comfortable to you. I'd prefer you to be comfortable and just ready to do it or whatever, as
All right.
opposed to making it comfortable for me.
Yeah, and I remember you sending the extra credit that one time when I was doing the other
Yes.
um what you call it. I still want to know if I was able to submit it because I couldn't submit it when I did it. It was
Yeah, was
locked.
that one of the problems where you're supposed to work something out and you just turn it in at my page? Do you
Yeah,
recall
it
what
was
week
at the
it's
end of the
in?
class or whatever. It was locked for me, so I couldn't turn it in.
Okay, do you recall what module it was or what it was called or anything?
I didn't even no I
The assignments now. I'll check. I might be able to figure it out. Let's see. First off, I got to find out what happened to 22 conceptual, which for some reason is not showing up. Oh, there it is. That's still a reason. It's just not published. Okay, so conceptual 22 should be good now, Micah. Now, as far as the extra credits go, I have Coulomb versus gravity. That was the one where you're supposed to calculate how strong the gravitational attraction between a proton and an electron are in a hydrogen atom, and then how strong the Coulomb force is versus the gravitational force. So that was one of them, and it did have a expiration date, so that could have been it. There was one where you divide by 243. That probably wasn't it, was it, Richard? Or I was Richard, or was it Kim? I think it was Richard.
for
Yep.
sure. I
Yep.
was yeah, I already did that, but I think it was the other one you mentioned. It was energy capacitor.
Oh, okay, gotcha. Yeah, let me see. Energy capacitor. That might have slipped over into an entirely different category. That's probably what happened. All right, well, I will look for that. Just send me those reminder words if you don't see it corrected by tomorrow. Just send me a text and just use that phrase. Just say energy of capacitor or something like that, and I'll be able to find it then. But I'm going to try to find it tonight and fix it. Hopefully, it'll be available to you tomorrow morning.
Yeah, I did it, but it just I just couldn't submit it.
Yeah, yeah. I'm just going to try to open it back up. So if you can open it back up tomorrow, you won't need to contact me. But no, I'm having a hard time finding it all.
All right, thank you. You have a
All
nice
right,
day.
all right. See you, Richard. Have a good one. Kim, are you still there?
Yeah, so I talked to you I think last week about
Uh-huh.
like taking the test because I was sick.
Right, right.
So I'm supposed to schedule this like tomorrow, and I gave the testing center a call, and they told me that you didn't put the test in yet.
Okay.
So
Did you want to take it tomorrow, you said, or were you trying to take it today or yesterday?
tomorrow.
Okay.
Okay,
I'll
so
set it up right now. I'll have to look up your student ID number unless you chat it to me.
I sent
Don't,
you an
don't,
email.
oh, you did? Okay, cool. It's Kim Wynn. That's cool. Yeah, I'll set it up for you for tomorrow. And
Got you.
I'll actually give you an extra day just in case anything goes wrong. You end up not being able to make it or whatever. I'll give you the day tomorrow and the next day.
Oh, okay. Thank you.
Okay.
All right, bye.
See you, Kim. Have a good one.
You too.
All right, hey Younger.
Yes.
Yeah, I had a question about that Lorentz from the earlier. Could you explain that? Yeah, because you went from like Q of E and then there's like that extra part inside of there now.
Gotcha.
It kind of you remember when we were doing like thermo and we started doing the one with like the A and B coefficients? I forgot what that was called. The Van der Waal,
Oh
like
yeah, yeah, the Van der Waal coefficient.
like account for certain things that kind of remind me of that.
Gotcha.
So
So yeah, the Lorentz force law is basically one we already knew was the force. Sorry, I'm writing on the screen right now, but it,
yeah.
for some reason just did something funny. So let me kill that. So we already knew one of them, which was the force on a charge Q in an electric field. E is F equals Q times E.
Mhm.
And we knew the other one was F is equal to Q times V cross
Cross
B.
B. Yeah.
Okay. So what the Lorentz force law is that basically the sum of those two. So it's QE plus QV cross B, but it's actually normally written. They just factor out a common factor of Q, and then just put E plus V cross B.
Oh, so it's just the sum. Okay, yeah,
Yeah,
that makes more
it
sense.
looks
Like
crazy because you got a plus with a
on
cross.
my notes, I
Right.
wrote it kind of weird. Well, it was a F equals QE, and then it was the arrow into like that final form. But for some reason, I thought it was like an equal. So I was like, wait, where did he get like the
Yeah.
Q
I was
times V
expecting you
from?
to do some kind of magic between the E and the.
Yeah, I was so confused. It's like, oh my God, what's this? Oh yeah, hey, I remember last week in your physics one class, you were talking about those Dover books. I went online, I got two of them. I got one in discrete math, another one in like graph theory.
Oh
And then
yeah.
yeah, I think over the summer I'm gonna try to have some fun with those because I'm supposed to be taking a discrete math course. I
Yeah.
signed up for one because I'm doing computer engineering. I showed it to my math professor. He saw the graph theory book. He started laughing. I was like, "Oh, is it like a bad book or something?" And he read the author's name and it was like, I didn't take this into like my grad program, like my master's
Yeah,
first
they
year.
have
I was like,
some
"Oh,
really
I
high
didn't know."
level
Yeah,
ones.
because I when I went to Virginia Tech to visit, I went to like the math booth and there's a faculty member there. I asked him like, "What do you think was like an interesting field?" It's like, "Oh yeah, graph theory. Like I do cryptology stuff like that." I was like, "Oh, sounds fun. Sounds
Yeah,
really
that's
neat."
tough stuff. Here's one of
Yeah.
the ones that I bought. This was
Uh,
mathematical analysis of physical problems, and it
mhm.
literally has like just about every physics problem you could imagine that
Oh,
can be
okay.
done in theoretical physics. So yeah, there I swear by them. And this one was uh 15.95. Look how thick that sucker is.
Yeah, like I was amazed by how many like pages there were. I think my discrete was upwards of 300, it was $13 or something.
Yeah,
So
yeah,
yeah, that
they're
was really
great
good
book,
value.
and the
Yeah,
binding's nice.
hmm yeah, I was gonna get like a multivariable one and like another linear algebra one, but I'm just getting these ones for now. So
You
I'm trying
said
to
you're
have
going
something to
for
read.
computer engineering, not
Yeah,
like
or double E, because
okay.
I see computer engineering like it's I guess easier than double E maybe because it's less physics. I don't know which one I want to get into, but I like the logic and hierarchy to computer engineering.
Yeah,
So
that's kind of nice. And
yeah,
the biggest
and
thing you'll learn, well, it used to be CMOS. I'm not sure that CMOS is even a thing that they paid much attention to
yeah,
anymore.
we haven't like touched on it all in my intro to computer engineering class.
Hmm.
So, but right now I'm really liking my circuit theory one class. But I haven't even taken like signals and systems yet. Like those are some meat classes. So
Yeah, that's where it starts to get a little robust.
yeah, I haven't even done like a lot of stuff with like electromagnetic fields or like what is it, AC circuits. So I don't know.
Right.
I'm just gonna wait after like the first 2 years, see which one I like more.